Fine. Good afternoon. Today we are going to look at the module 4, where we are going to handle multicast routing protocols and ad hoc wireless networks. As such, in module 3, we were looking at routing protocols for ad hoc networks, and we primarily were focusing on unicast-based routing, which means is one single source which is trying to reach out to one single destination. And so here again, we know what's all the problems that we have in ad hoc networks. And we were trying to address routing protocols under several categories, each one with different approaches. So today we will take up, one of the major application demands of where many applications of ad hoc networks, as you are aware, may need multicasting. So the routing protocols accordingly has to address to the demands of multicast. The outline for today's lecture is going to be this. We are going to understand the challenges that are involved and the issues that we need to address while you design multicast routing protocols, specifically for ad hoc networks, because we are moving from wire to wireless networks. You know that there are major challenges that actually comes in with respect to the route maintenance and all that. So we are going to look at how multicast routing protocols can operate, what are the different operations of it, the classifications, though we are not going to be much in depth of the lots of protocols that have been proposed in the literature, but we will try to understand the different classification that it basically has. And as such, they've come up with an architecture reference model of how you need to basically address layer-wise in terms of multicast routing design. So then we will get on to one classification of multicast routing protocol, which is called a tree-based routing approach, multicast routing approach. Under that, we will see something called as a bandwidth efficient multicast routing protocol, which in short is called BEMRT. Okay, so basically the outline for today. As you are aware, ad hoc networks, it's a dynamically changing topology where you don't have any infrastructure and all that. The wireless links are basically really constrained in terms of its bandwidth. The nodes are constrained in terms of the energy. And the channel is again error prone. So you have all these issues which actually makes your routing engine. So, but ideally, we know that multicasting is one major efficient way of transferring messages, transferring the same messages to several receivers. That's the entire idea. So this is just an example where we can understand multiple unicasting and multicasting. So one-to-many communication, is literally multicasting. But here, you have for same message multiple results. If you're literally doing multiple unicasting by addressing individually the same message to each of these um, you know receivers, then ideally see it needs 8 transmissions as per the scenario to reach out to 3 receivers. So our entire idea is this, the same message being to be communicated to many receivers who are expressing interest to join the multicast group can literally be addressed as one same message, a single message, and then routed in such a way that you reach out to all these potential groups of multicast groups, right? So that's the entire idea. From multiple unicasting, we wanted to move to multicasting, where appropriately these routers are going to do this multicast, where it knows the path to basically reach out to the receivers of the multicast groups. So you see that there are just 3 transmissions in this picture when compared to the 8 transmissions that you saw. So that's going to be really, really efficient in terms of transferring messages, where many applications demand multicasting. That's the entire idea. So multicasting in ad hoc network, as you say, you know that the bandwidth is limited, and you can't afford multiple unicasting. And more appropriately in ad hoc networks, where you have battlefield scenarios, search and rescue operations, for all these you basically need one-to-many communication. So people thought, why not we have multicasting routing protocols being designed. And when you compare to wired networks, you know that we have such an error-prone channel, and so that's going to be having low link reliability in terms of its packet delivery ratio, and the mobility is actually going to break your range. Your link breaks because of these mobility, and then the energy consumption aspect as such is going to drain the energy of the nodes. So all these are the extra problems that you're going to have compared to a traditional multicast routing protocol that you design for wired networks. So we will have to have something proactive, reactive approaches like the same unicast design that you saw, but in addressing the same message to receivers. Okay, so having said that, multicast routing is communication among a given set of nodes, and you know that it's going to be better than multiple unicast. So generally, when you see what we do here is we try to maintain a routing tree for a multicast session. So routing tree basically means that there's going to be the root of the tree, which ideally is going to be the source, and the receivers, which are the leaf end of your tree. So we'll have to form a routing tree, which is also called as an acyclic graph or acyclic graph, meaning it's a tree, right? You don't have a cycle. And it's an acyclic spanning tree. Spanning tree meaning you try to reach out to all the nodes without any cycles. And such a way these trees are maintained in such a way there's a separate path for each of your receiver that you basically have. Now this, they say, is not going to be appropriate for ad hoc networks, as you know that the tree can easily break if you have just one path being maintained, right? A single path between a source and the receiver is going to be quite susceptible to link breaks, and your PDR can go down. So people started to think of how we can achieve high packet delivery ratio despite you design for ad hoc networks. So that was the entire focus that actually came in. So this is the idea: the trees can break due to the highly dynamic topology, and so here the idea is in a spanning tree where what happens, the packets are sent to all the nodes in the tree, which means they traverse each and every link only once. So you are trying to have a path being maintained, but that can actually break. So the entire multicast tree structure is not going to be stable, and it needs to be reconstructed continuously as the connectivity changes. So you'll have to be more proactive enough here of whether are you going to prior hand ensure that you have some prediction mechanism, or are you going to react it only when you detect that there's a break. All that is something which we'll have to start addressing. This is going to incur more control traffic and processing overhead due to frequent exchange of routing vectors, link state tables. So just imagine that you have something like this traditional distance vector approaches where you're going to exchange tables and all that, right? That's going to be additional traffic that you basically have, and so we are going to look at all these issues that we need to address while you design a multicast routing protocol specifically for ad hoc wireless networks. So considering all the challenges that we have with respect to the limited bandwidth, the error-prone shared broadcast channel, the mobility of the nodes, the limited energy availability at the nodes, the hidden terminal problems that exist, and how the MAC addresses the security issues that you basically have. What we'll have to first start doing is design a routing protocol which is quite robust. So what do you mean by robust? Meaning despite the mobility of the nodes, where you know that the link failure is going to be common, which can lead to a very low packet delivery ratio. Our goal here is to sustain such mobility and ensure that you achieve high packet delivery ratio. So that's the first thing. The second issue that we'll have to address here is how efficient is our multicast routing protocol design. So I'm going to define now, as you know that in terms of the bandwidth efficiency, we'll have to address it. So multicast efficiency, if you need to design, if you need to define it as a ratio, this is the definition. So the multicast efficiency is defined as the total number of data packets that is received by the receivers, right? And total number of data and the control packets that is transmitted in the network. So you assume that you are transmitting 100 data packets, and you know that all the 100 packets is being received, then it's a 100% PDR. But how do you define in terms of multicast efficiency is the extra control packets that you are going to spend to maintain these multicast group members, right, and form this multicast grouping, is what we literally have to say. Uh, Multiple unicasting is another case, but you also have to look at the condition, right? Under source initiated operation, we are going to follow an approach called either soft state maintenance approach or hard state maintenance approach. See, the logic is simple. Now, just look at an aspect where we know what's soft handoff, what's hard handoff, right? So, hard handoff meaning you literally detect that there is a link break and then you go on to repair your rules, right? That's called a hard approach, whereas a soft approach is something where you do not ensure such kind of drops or link breaks happen. So periodically, in this case, when you apply to multicast, we are ensuring a soft state maintenance approach, meaning we are going to form either a multicast tree. uh, so let's understand what's tree. So you have a tree maintained per multicast group, say for example per source. So every source tries to maintain a multicast tree to all the receivers, or a mesh, meaning you have a kind of a graph itself, multiple paths to reach out to receiver. So you'll have to keep updating this, ensuring even if the nodes are moving, the links are breaking, you still have the tree or the solutions impact, right? So how do you ensure that it is a impact is intact? Is basically that you'll have to periodically exchange such a way that you maintain the tree. So what we have to do here is that's a source initiated approach where the source, right, is the one who periodically, now you'll have to first have the group members or the members who want to who's interested in joining the multicast group. So how do they do is, first the source goes on to either advertise, right, periodically flood, asking for you want to join my group. So he goes on to periodically flood join requests throughout the network, and whoever receives, and the receiver which actually wants to join the group will express their wish to actually receive. So they go on to send the joint reply in the reverse path of the joint request. So when this kind of root request root reply you're seeing, right, so that's similar to this joint request and joint reply that initially comes in to form the multicast group. So you construct a tree there, right? So when you construct the tree there, every node which is actually rebroadcasting or sending the root reply backs has to maintain some state information regarding the multicast group. So there is where we are going to maintain the forwarding states in the intermediate nodes that are part of the tree or the mesh, right? Where they're going to maintain which all receivers have expressed interest, and the multicast group that is in turn being formed because of that. That state information is actually going to be maintained. And so if I want to basically reach out to this multicast group, I'll have to forward to the appropriate next stop node. And so what happens is that you periodically, the source keeps on flooding joint request, and receivers goes on to express their wish to receive the joint reply by sending the joint reply messages, right? So this kind of an approach is called a soft state approach, where it's all about the root discovery process that happens for the multicast. And in turn, since you periodically keep flooding, you're going to maintain those routes even if there is a failure, right? So that's the source initiated approach of soft state maintenance approach. Whereas the other opposite of this in the source initiated approach itself is the hard state approach, where you're not going to periodically keep updating, exchanging control packets to maintain the tree, or anyone to add it. You basically have an explicit root repair process. Only when you detect that there is a link break, right, your tree has to be reconstructed back. So the one node, either the upstream node or the downstream node I can call, which basically means that the one which is closer to the destination can be called as an upstream node, right, are the one who actually sends it down is basically called the downstream node. So what happens here is when any of these nodes actually detect a link break, they can explicitly try to repair themselves, instead of involving the other nodes that are there, right? So that's basically called hard state approach, which can actually spend a minimum amount of control packet overhead, in order to maintain. So, but yeah, you know that this is quite a reactive approach of maintaining the tree. So that's a source initiated approach. Soft state multicast, if you basically see, as you see that there is protocols. In this is the hard state multicast where you don't see any refresh period come. Okay, so operation we saw in terms of the source initiated, but there's another way in which you can actually form multicast groups is where, see, you as a receiver are interested in joining a group. So what you can do is you send that specifically flooding asking for that I want to basically join, right, to part of the group. So the thing here is either you'll have to get associated with the source, or you anyone in the group who's already there can reply you back telling, hey, come on, you can use this path. So that's the entire idea, where entirely a new group that you want to form, the receiver starting to express joint request, flooding request, and then you get a reply, and then you try to acknowledge to that. So this is going to be some three-phase process that basically happens, where the source node or the node that is already part of the tree or the mesh is allowed to respond to the joint request that comes in. So the point here is the receiver sends a joint request, that it wants it's sending a joint request to join to the group, and the source or the other nodes replies back, right? And the receiver now can get multiple replies that it has to now choose which path it has to basically take, and so it acknowledges the path which is having, say, the smallest hop count by sending a packet called as join acknowledgement packet. Now this is a three-way handshake process compared to the source initiated where you saw a two-way handshake process. But here again, the route maintenance can be periodically initiated by the receiver, where the receiver, again, it's a soft state, meaning periodically you will have to start exchanging the joint request packet that is there. Whereas in a hard state approach, the downstream node will actually search for the route to the multicast tree upon the link break. Okay, so that's basically going to happen. The parent is actually has to search, right, to associate itself to the tree in an and not periodically, send packets in waste and create additional overhead. So that's the initiated operation that is there. So if you see this, it's just the reverse approach that has come in now. Uh, Whereas in a hard state, you're not going to periodically send the idea behind operation of multicast routing protocol. Source initiated, receiver initiated, soft state maintenance approach, or hard state maintenance approach. The classification, what they do here is they classify broadly as application independent or generic multicast routing protocols, or specifically application dependent multicast routing protocols. As you're aware, say for example, application dependent, meaning some are really time sensitive applications, then you will have to specifically have your multicast design protocols to ensure certain things. So that's the way they broadly classify. And based on application independent generic, you have either unicast routing protocols. So don't worry looking at this picture. This is the top, level application of multicast. So based on topology, tree based, if I say there's only going to be a single path between the source and the receiver pair, right? We are talking about pairs here, the source and the receiver pairs. The source tree based, multicast routing, or shared tree based multicast routing. If you see in source tree, there is a tree rooted at the source. So the source node is the root of the node, and then you try to maintain a tree, which is your group members of the multicast. So if anyone wants to in turn become a source for that multicast group, with respect to the source, you'll have to construct a multicast tree. So please understand that, right? So the traffic distribution is going to be performing better because you have separate paths between the source and the receiver pair that you basically have. That's the idea that we are literally talking here. But we also have another better way called as shared tree. What we are trying to do here is we are trying to form a common tree for all the sources that belong to the multicast group, which means multicast group anyone can potentially become a source. So instead of constructing a separate source based tree to all the group, you can have a common tree where the root is not the source but the root is the core node, right? So it is via this core node all the tree members are connected, right? And so what's happening here is the number of exchange that happens gets reduced, and you maintain a shared tree approach, which is quite scalable compared to that of that's a source-based tree approach. So if the core node fails, but however, that's going to become a problem. You'll have to start reconstructing it. But this is quite a scalable approach that you basically can have compared to a lot of trees that you try to create with respect to every source. Another classification is the mesh based, where you understand that between source to receiver, you have more than one path. So due to availability of multiple paths, you say that you are addressing the robustness of the design that you basically have. The classification. So let's look at tree based multicast. Now here you have the S1, where here being maintained from the sender to the receiver along a single path. So that single path is what we're talking, right? So if a tree here breaks, a source space tree breaks, then it's going to become a problem that you can go to understand here. Whereas a mesh base, if you see, it can actually flow from sender to the receiver along multiple paths. So despite failures, you still have the state information being maintained by the other nodes, which can actually help you to achieve a high packet delivery ratio. But you do understand that this is going to have a higher overhead, right? So that's the mesh-based idea. Now, this is a comparison chart between the source tree and the shared tree approach. Now, source tree, if you basically see, per source, you are going to maintain a single multicast tree. Whereas shared tree is something where all the sources in that potential multicast group is going to maintain a shared tree, right? So the ultimate idea is the root is not the root node is not the source node, but a core node which connects all these members. That's basically there. So he's actually going to be quite loaded. But if you see that this is quite scalable, because when you have more multicast sessions, more sources, more trees that you create, it's going to create degradation in the performance, which is not going to be there in the shared tree approach. So it's more scalable compared to source tree based approach, which is, since it's not going to affect the bandwidth of that. But the problem here is, in source tree, again, you will have to have more memory being maintained at the source node, as since every node has to maintain the multicast group information and all this for the tree it tries to maintain, right? So per multicast group, per source, each one has to maintain the state information. Here we are trying to share the information between the sources, and lesser memory is actually required. So that's the this that they try to say here. Based on the initiation, we saw it's source initiated or the receiver initiated. Based on the topology maintenance, we said it can either be soft state, where control packets are flooded periodically to refresh the route, and you achieve a high packet delivery. Whereas here in hard state, you only during a link break you go on to flood control packets and work out on the link failure. Problem here is low control overhead, quite efficient, but packet delivery ratio becomes a quite a worrying factor. So we'll have to see what is the trade-off trying to approach here, right? So tree-based multicast, the problem here is it's not robust to operate in highly mobile environment, but the multicast efficiency is going to be high because you literally have overhead that you basically see there. So let's quickly get on to one of the multicast routing protocols, which is called bandwidth efficient multicast routing protocols, which is specifically designed for highly bandwidth scarce environment. And the key design criteria, as you see, is the bandwidth efficiency. So ultimately what they try to do here is, let's try to reduce the number of data packet transmissions that you literally are trying to do, either in terms of the redundant transmission that we're talking, or the more nodes being participating there. So what they did is they followed the hard state approach, where only when link break is there, they try to work out, so that the control overhead, because it's a bandwidth efficient approach, they had to follow the hard state approach, and to save bandwidth, they avoid this periodic transmission control packets that is there. So there's another interesting aspect in bandwidth efficient multicast routing protocol, which is the route optimization. Route optimization is basically, suppose you are moving, right? Because of the mobility, your tree is going to break, as you are aware of, right? But you can in turn say is moving closer now to the tree, towards the source. Now all the other nodes can be cut off, right? Unwanted forwarding nodes can be cut off, so that it basically becomes more of an optimized route, and you can avoid a longer route that basically comes in, right? So you can avoid reduce the data packet transmission that comes in. So this is one of the optimization procedures they follow in the bandwidth efficient multicast routing approach. Here again, there are two phases. One is the tree initialization phase, and the other is the tree maintenance phase that comes in. Since it's an hard state approach, we'll have to understand that the maintenance is basically hard state. But the initialization approach that we see here is the receiver initiated approach, where the receiver goes on to send joint packets by flooding the joint control packets, and the reply comes from the existing members of the tree or the source itself. So they're going to respond back with the reply control packets. And when many such reply packets comes in, then the receiver can actually select the one with the minimum hop count and send a reserve control packet to the member node. So it's basically a three-way handshake. Join request reply coming from the intermediate nodes who already have the multicast tree maintained or the the source, and then finally this guy goes on to acknowledge by sending information across the path that actually comes in. So this is an example where say R3 wants to join the multicast group, and then the maintenance phase is where say R3 moves from but yeah, that's not good in terms of the PDR, but it's efficient in terms of the bandwidth that comes in. So there's another thing where instead of the upstream node trying to find out, there's something called the local region. Thanks for listening. So that actually ends this